Have you ever stopped to think about how we take something as simple as spinning, just motion, and turn it into the electricity that powers our entire world? It's incredible, right? From our phones to our cities, it all comes down to one amazing invention. So, let's dive in and uncover the magic behind the electric generator.
I mean, it sounds almost like science fiction, doesn't it? The idea that just rotating a wheel can create this invisible force that lights up a skyscraper miles away. Well, that's the big puzzle we're going to solve today. And the answer, you'll see, lies in this beautiful dance between two of nature's most fundamental forces.
Okay, so before we can even start to build our generator, we've got to understand what it's actually making. So let's start with the absolute basics and pull back the curtain on electricity itself. What is that invisible power that's flowing through the wires in your walls right now?
At its heart, electricity is just the movement of these unbelievably tiny particles called electrons. The easiest way to think about it is like this. Imagine a copper wire is a pipe, and the electrons are the water just sitting inside. The whole goal of a generator is to get that water moving in a powerful, directed stream.
Now, if you could zoom in way down to the atomic level, you'd see something pretty wild. Inside that copper wire, you've got millions of what we call free electrons, and they're all just zipping around randomly, in total chaos. But when we apply a force, and scientists call this force voltage, we can organize that chaos. Voltage is like the pump that provides the water pressure. It gets all those electrons to stop messing around and start marching in the same direction. And that organized march, that is an electric current.
So we know we need to push electrons, but what's actually going to do the pushing? Well, let's meet the second key player in our story, magnetism. You know, it's this totally invisible force, but trust me, without it, our modern world just wouldn't exist.
You see, every magnet is surrounded by these invisible lines of force, creating something we call a magnetic field. These lines always flow out from the magnet's north pole and loop back around to its south pole. And even though we can't see them, they exert a very real push or pull on certain things, including, and this is the important part, on our little friends, the electrons.
And this is where things get really interesting. It turns out that electricity and magnetism aren't separate things at all. They're basically two sides of the same coin. When you run an electric current through a wire, that wire creates its very own magnetic field. This incredible link is called electromagnetism.
So what does this mean? It means we can create a magnet that we can turn on and off. It's called an electromagnet. And there's even a handy little trick to figure out how it works. It's called the right-hand rule. If you wrap your hand around a coil of wire with your fingers pointing in the direction of the current, your thumb points to the North Pole. It's that simple. And the more current you use, the stronger your magnet gets.
Okay, quick recap. We know an electric current can create a magnetic field. But our goal is the exact opposite, right? We want to use a magnetic field to create an electric current. This is where the true genius, the real spark of the generator comes to life.
This is it. This is the aha moment that changed everything. Back in the 1830s, a scientist named Michael Faraday figured, hey, if electricity can make a magnet, maybe a magnet and some motion can make electricity. And he was right. By just moving a wire through a magnetic field, he forced the electrons inside that wire to start flowing. No battery needed, just motion. This wasn't just some clever trick. This was the discovery that would literally light up the world.
This incredible principle is called electromagnetic induction, and it is the single most important concept to understand. It's the beating heart of every generator on the planet. And the key word here, the one you absolutely have to remember, is changing. The magnetic field has to be changing relative to the wire. You can move the wire, or you can move the magnet. As long as there's relative motion between them, you will generate electricity.
So how do we turn this principle into a real machine? Well, it all boils down to two main parts. First, you've got the rotor. Think rotating. This is the part that spins. It's our electromagnet. Then you have the stator. Think stationary. This is the part that stands still. It's just a bunch of copper wire coils. So we spin the rotor, its magnetic field sweeps past the stator's wires, and boom! Electromagnetic induction kicks in and creates an electric current.
And believe it or not, there's another handy rule for this. It's Fleming's right-hand rule. With your right hand, if you point your forefinger in the direction of the magnetic field and your thumb in the direction the wire is moving, your middle finger will point exactly in the direction the current is going to flow. It's the physics that makes this whole thing work so perfectly.
So we're creating an electric current, which is awesome, but it turns out there are two different flavors of current that a generator can make. You've definitely heard of them, AC and DC. Let's break down what they are and how a generator can cook up each one.
Think about that coil spinning inside the magnetic field. For the first half of a turn, one side of the coil is moving up while the other side is moving down. Then they switch. Because of this, the direction of the current that gets created naturally flips back and forth over and over again. This is called alternating current, or AC, and it's exactly the kind of power that comes out of the outlets in your home.
So how do you get that alternating current out of the spinning machine? Well, an AC generator uses two simple, continuous metal rings called slip rings. Each end of the wire coil connects to one ring. As the whole thing spins, brushes stay in contact with the rings, and that back and forth current just flows right on out into the circuit. Simple and effective.
But what if you don't want the current to switch directions? What if you need a steady, one-way flow of power? Like the kind you get from a battery. Well, that's called direct current, or DC. And it's absolutely essential for things like charging batteries and powering almost all of our electronics.
Now, the key to making DC power is this really ingenious little device. Instead of two full rings, a DC generator uses one ring that's been split in half. It's called a commutator. Here's the brilliant part. Right at the exact moment the current in the coil is about to reverse, the brushes cross the gap and switch contact to the other half of the ring. This cleverly reverses the connection on the outside, which forces the output current to always flow in the same direction. It's like a perfectly timed mechanical switch.
All right, let's put it all together side by side. AC generators, they make a current that alternates using simple slip rings, and they're perfect for sending power over long distances to the grid. DC generators, they make a one-way current, thanks to that clever split-ring commutator, which makes them ideal for batteries and electronics. It's two totally different outputs, all from one amazing scientific principle.
Okay, so we've mastered the science, but how does this connect to our actual lives? Well, the exact same principle we just explored is used to power everything, from a tiny hand crank radio all the way up to entire continents. The only real difference is the scale and what we use to get things spinning.
The fundamental challenge of generating power is always the same. How do we spin the generator? In a giant hydroelectric dam, we use the incredible force of falling water. In a thermal power plant, we burn fuel or use a nuclear reaction to boil water into high-pressure steam that blasts a turbine. And out in a wind farm, we just let the wind itself do all the work. All of these massive energy sources are designed for one simple goal: provide the mechanical energy to spin a rotor inside a stator.
Whew! Okay, we have covered a lot of ground here, from tiny little electrons to massive power plants. So to make sure it all sticks, let's wrap this all up with the 5 most important takeaways from today.
Here we go. Number 1, electricity is just electrons moving together in an organized way. 2, that flow of electrons creates its own magnetic field. 3, and this is the big one, if you flip that process, moving a magnetic field past a wire, you create an electric current. 4, that's exactly what a generator does. It turns mechanical spin into electrical flow. And finally, number 5, with a small tweak in the design, that generator can produce either AC power for our homes or DC power for our batteries.
And that's really the power of understanding all this. The next time you flip a light switch, you'll know the incredible journey that energy took, from falling water or superheated steam to a giant spinning magnet to a flow of electrons traveling for miles just to light up your room. The science isn't magic, but what it lets us do, well, that feels pretty close.